Hello everybody, thank you for tuning in for this talk on signal processing and random walks and graphs in SIMPLICIAL complexes. Before starting, let me thank the organizers for giving me the time to present this work here, and let me thank my collaborators Santiago Segarra, Austin Benson, Quentin Gia, and Ali Jababai. So this is going to be about signal processing, which is a rather different topic to what we've heard before. So let me start by recapping some central notions from signal processing so we're all on the same page. Of course, signal processing is actually a huge area, so I've compressed things a lot here, and I'll basically just give you a two-slide introduction. So let's talk about signals first. The central mantra of signal processing is to think about any observed data as a composition of signal and noise. Now, of course, this begs the question, how do you define signal and noise? And this is basically the key modeling question we have to address if we want to do any kind of signal processing. In the context of time series analysis, the classical assumption is to say the signal, that's the part of the data that varies smoothly, or it has low frequency components if you wish. And accordingly, the noise is the part that changes rapidly or has high frequency components. So much for the signal and noise. Now let's talk about processing for one slide. Let's think again about the data in terms of the signal S plus the noise term eta, and say our task is now to recover the true signal S from the noisy measurements Y. If we confine ourselves to linear filtering, then we can basically multiply the signal Y with any matrix that we choose in order to estimate the original signal. So a useful idea here is to think about this linear filtering as a sequence of three steps. First, we project the signal onto some basis vectors that we choose. Second, we amplify or decrease certain components of the signal in this basis. And finally, we transform the signal back into its original domain. If we consider time series again, then these steps would typically correspond to using a Fourier transform to express the signal in the frequency domain, which is to say we've chosen Fourier modes as our basis function. Then, second, we modulate certain frequencies. For example, we remove the high frequencies. And then, third, we pull back the signal into the original time representation. So now let's consider signal processing in graphs. How could this be done? Well, let's first observe that we may think of signal processing in classical domains, such as time, as processing data that's defined in domains that can be represented by a regular graph. So we may think of signal processing in discrete time as defining values for each of the nodes in the simple line graph as depicted here. Image processing, accordingly, becomes the processing of data that's defined in the nodes of a lattice, of a regular grid. And accordingly, video processing corresponds to processing a sequence of grids, so that's a tensor network structure. Okay, let's now consider signal processing in discrete time in a bit more detail from the point of view of the underlying graph. For simplicity, we will represent the time domain here now as a circular graph that wraps around at the very end. And now let's look at the graph Laplacian of this. The graph Laplacian of this graph will be a circulant matrix. And now this is very nice for the following reasons. The eigenvectors of this graph Laplacians are actually Fourier modes. So we can recover the classical Fourier modes by looking at the spectral decomposition of the underlying graph. Now this leads to the following idea of how to define signal and noise in a graph. A smooth signal is a signal that can be expressed as a linear combination of the eigenvectors associated to small Laplacian eigenvectors. So here say this again, smooth signal is a signal that has dominant contribution from the slow eigenmodes of the graph Laplacian. And accordingly, a noise signal is one that can be expressed by eigenvectors that correspond to high eigenvalues of the graph Laplacian. How can we use this? let's look at an example. Here we look at the task of smoothing an interpolation of graph signals. So we consider signal y, for example, defined on 2 points here, on 2 nodes of the graph. And what we want to do, we want to smoothly estimate a signal that interpolates between these. We can do this by optimizing the following problem. We first want to find the y-hat that is as close as possible to the original observation in true norm, and we add this quadratic Laplacian regularizer here. Turns out that this has an explicit solution that can be expressed as a linear filtering operation. So it's a matrix times the original observed signal. So now, how does this quadratic term ensure that we get some smooth signal out of this? Well, if we write out the quadratic form, we will see that's basically a sum of squares here. So the cost will be high if 2 nodes that are connected have very different values. If the nodes are not connected, we don't care about the difference. So you can think about this as a total variation along the edges of the graph. If 2 nodes are connected that have very different values, then this is a high cost. This is not very smooth. And of course, there's a minimal cost here for the constant signal. And the cost here is basically 0. So let's look at an example here. These are the eigenmodes of like a toy graph that I've crafted. And we can see that the eigenvalues basically give a good indication of how smooth the signal is. So from the left to the right, we have increasing smoothness. On the right, there is a constant signal, which is always an eigenmode of the Laplacian, and this is as smooth as it can get. So what about signals defined on more general complexes now? Well, let's first consider the case of data defined on the edges of a graph. If we consider data that describes some kind of flow, for instance of traffic or information, then this kind of signal is typically associated to the edges rather than the nodes. So the question is now, how can we use the node-centric tools that we just learned about to analyze such kind of data? If you know a little bit of graph theory, you might say, hang on, I know a trick here we can apply. Let's look at the line graph transformation. And this works as follows. Every edge in the original graph becomes a node in the line graph. 2 nodes in the line graph are connected if the corresponding edges in the original graph shared an endpoint. So for instance, edges A and E become nodes in the line graph, and they are connected in the line graph as they are both incident to node 4 in the original graph. Using this line graph transformation, we can now represent any edge flow data as node data on the line graph. And then we can use our graph signal processing tools to analyze this data. This is the idea at least. So now let's look at a concrete example given by a simple conservative flow in a small network, such as the one depicted below on the left. We cannot observe the true flow, but we get to see a noisy version of the flow, as shown in the middle, and our task is now to estimate the true edge flows. Using the line graph trick, we can now, of course, transform this problem into a node signal filtering operation and estimate the true signal using a filter based on the line graph Laplacian, as shown here. If we do this, however, it turns out that the signal we estimate is actually further away from the true flow as our initial measurements. So we actually made things worse rather than better with the filtering. So what went wrong here? Well, it turns out that for flow data, such as the one we considered, the type of smoothness the graph Laplacian encodes is actually not a good model for the signal. When we run our filtering operation with the line graph Laplacian, we basically penalize if 2 adjacent edges in the original graph have a different flow in them. So we perform some kind of local averaging. However, a single flow might, for instance, get split between 2 pathways, which is actually what happens in our example. What is essential for flow signals, what makes them continuous and smooth, is not that adjacent edges have a similar value of flow, but that we have a conservation of the total flow. So this means that we do not need an operator, such as the line graph Laplacian, that keeps track of local deviations, but we need an operator that keeps track of flow conservation. Luckily, there is actually such an operator, and it's the HODGE 1 Laplacian. In the special case of a graph, which is a simplicial complex without faces, this reduces to the edge Laplacian. Importantly, the null space of this edge Laplacian is actually the cycle space. So the eigenvectors with the smallest eigenvalues are actually cyclic flows, which are of course perfectly conservative. So now, if we apply a linear filter based on this edge Laplacian to our noisy flow data, we see that it works out fine, and we actually get an improved estimate from our measurements, which is great. However, it turns out that this is but one example of a larger theme that I want to propose here, which is based on the HODGE Laplacians associated to simplicial complexes of any dimension. So what's the general theme here? The general theme is that the spectral decomposition of the general HODGE Laplacian, as written out here, offers an appropriate notion of smoothness for signals defined on any simplicial complex. More precisely, the claim is that the HODGE decomposition, which can be written down for the space of simplices of any dimension, offers a great set of basis functions to consider for signal processing on general complexes. For instance, in the case of edge flows, the HODGE decomposition says that any flow can be decomposed into A, a set of acyclic gradient flows, B, a set of cyclic curl flows, which are associated with higher order phases in general, and C, a set of harmonic flows, which are associated to the holes in topological space we consider. Now let's look at a concrete example. We use again the same toy graph as before, but now we plot the eigenfunctions of the edge Laplacian here, again with the more smooth functions towards the right. And as promised, the smoothest functions are actually the two possible cyclic flows, as we can see here. And the more we go to the left, the more acyclic the flows become. So let's recap the big picture quickly. And we have seen that signal processing on graphs can be seen as a generalization of classical signal processing techniques. I have also argued that the HODGE decomposition and the HODGE Laplacian provides us with a good set of basis functions and accordingly with a notion of signal and noise for data defined on simplices of any order. Finally, what I have not shown so far is some applications to simplicial complexes with high order phases such as two simplices. So let's look at this now. Okay, at this point let me switch gears a little bit. Just like we can look at the normalized graph Laplacian or random walk Laplacian for graphs, we can actually define a normalized HODGE Laplacian. Now, if you choose the weightings appropriately, we actually can show that this can be related to a random walk on a simplicial complex. But I will not talk about this further here. Instead, let's focus on an application of such a normalized Laplacian, namely the equivalent of the so-called diffusion maps for simplicial complexes. Okay, let's first recap what diffusion maps are on graphs. If you have a diffusion process on a graph, you can write it like the following difference equation. Now we can use the spectral decomposition of the propagator matrix that appears in this equation. If we then simply transform every unit signal defined on a single node using these eigenvectors, we obtain a representation of every node according to the so-called diffusion map. Note that from the point of view of signal processing, this is actually simply the frequency domain representation of the individual node signals. Now the nice thing is that one can use this representation as a low-dimensional embedding of the nodes, or we can perform spectral clustering based on this. For instance, we can only keep, let's say, the k lowest frequencies and plot k-dimensional embedding according to those eigenvectors. So let's try to adapt some of these ideas to edge data defined on a simplicial complex. For this, we consider the following example. We have a simplicial complex on which I've defined some edge flows, as shown here. And even though I have not drawn it, all the possible 2 simplicities are present here. So we've filled all the possible triangles. Nonetheless, there are still 2 holes left in the simplicial complex, which correspond to the harmonic functions. That is, the 0 eigenvectors of the corresponding Hodge Laplacian. So let's plot those 2 eigenvectors here on top of the complex. We see that each of these eigenvectors is essentially encircling a single of these topological holes. The first is encircling the lower hole in counterclockwise direction. The second is encircling the upper hole in the clockwise direction. Moreover, the flow is in the same direction in the central path for both of these harmonic forms. So we can now project the flow of each edge onto those 2 eigenvectors, just as we did with diffusion maps. And we will get a picture like this, which basically tells us how the flow on each edge behaves with respect to these harmonic modes. So for instance, the flow on all the edges in the lower left is basically aligned with the counterclockwise rotation of the first harmonic mode, but it's anti-aligned with the second. The edge flows in the middle are anti-aligned with both harmonic modes, and the edge flow on the upper right are mostly anti-aligned with the first harmonic and aligned with the second. So if we plot these kind of coordinates in 2 dimensions, now we get a picture like this, which one can use, for instance, for topology or edge clustering, as we will hear more about in the next talk, I believe. But of course, we don't have to stop at single edges, but we can consider whole trajectories as edge vectors and project them into the harmonic space as well. The interesting thing here is that even though the trajectories look actually relatively different, they'll be embedded together because they behave topologically in the same way with respect to the holes in the complex. So for instance, the red, green and orange trajectory here end up having a large projection into the first harmonic mode, but only a very small one onto the second. So that corresponds to the fact that they all pass to the left of the lower hole. But of course, we can also use these tools not only for synthetic data, but to classify real-world trajectories as shown here. So in this case, the data is provided by some buoys that drift in the ocean around Madagascar. We construct a simplicial complex here by basically parcellating the space into some hexagonal grid, and then we construct the simplices according to how many buoys flow around these particular areas. For instance, Madagascar then becomes a hole in this space because Madagascar is not water but land, and so no trajectory can pass through this. So once we've done this, we can now project each of the buoy trajectories into the harmonic space and color the trajectories accordingly. And what we get from this is basically a segmentation of the trajectories in 2 classes, with those that are coming from the east and pass by Madagascar in a sort of counterclockwise fashion. Those are plotted in red here. And with those trajectories that come from the east and move south and around Madagascar. And those are the ones plotted in blue. And for more details about all these constructions, I will encourage you to have a look at the publication associated to this work. It just got published in SAM Review this year, and you'll find all the construction, all the details about the projection, etc. in there. Now, let me wrap up. We've seen that signal processing on graphs and complexes can be seen as a natural generalization of classical signal processing tools. And a central role here was played by the Hodge Laplacian and the notion of signal and noise it induces. Basically, the eigenvectors associated with small eigenvalues are what constitutes the signal. They are smooth. The eigenvectors associated to high eigenvalues will be what we consider noise. I haven't talked about the random walk interpretation of the normalized one Laplacian, but feel free to ask me in the questions. I've shown you a couple of examples for how the signal processing tools can be used. We've seen how we can filter flows in the cycle space. We have also seen how we can derive low-dimensional representations of trajectory data and how we can use these for clustering. So there's actually a lot more here. So for example, based on these ideas of defining a simplicial diffusion, we can define a notion of page rank for simplicial complexes and edges on simplicial complexes. And this is something I haven't talked about here, but feel free to ask me in the questions as well. But before going there, I just want to briefly flash the publications on which this work is based, which is three main papers that you might want to read.